Hello, in this video I'm going to give you a short overview of the most important aspects and results of our research work titled Stochastic Methods for Handling Uncertainties in Automotive Applications. My name is Alexander Wasserburger and I'm working as a postdoc in the Christian Doppler Laboratory for Innovative Control and Monitoring of Automotive Powertrain Systems. The Christian Doppler Laboratory is a 7-year research project under the lead of Christoph Hammetner in cooperation with our industrial partner AVL List. The most important research directions are the modeling of powertrain components like batteries and fuel cells, power hill testing and calibration under real driving conditions, and also the predictive multi-level control and operating strategies for entire vehicles. In my research, I'm dealing with the calibration of powertrains, like for example engines, under real driving conditions. The motivation behind this research comes from typical shortcomings in current state-of-the-art calibration workflows, where most of the time varying operating conditions, different drive cycles and other uncertainties like traffic conditions or weather conditions are simply not considered. This then leads to higher than expected consumption and emissions in real-world operation, which in turn then requires manufacturers to perform excessive real-world testing, especially in the context of real driving emissions, RDE, but also in terms of the safety of advanced driver assistance systems. Therefore, the goals and also the contribution of our work is the introduction of stochastic optimization formulations for automotive calibration. This involves the inclusion of uncertainties directly in the optimization, the formulation of adequate optimization goals, and also the efficient approximation of the involved statistical quantities. Here you can see an overview of the related topics and also the proposed solutions. On the left-hand side, you can see the considered topics and systems, ranging from the component level up to the platooning level. On the right-hand side, you can see the considered uncertainties and disturbances, like actuator tolerances, drive cycle uncertainties, or communication loss or delays. On the bottom, you can see how all this is connected with our stochastic optimization approach, where we achieve emission threshold violation control, low energy consumption, and efficient and safe transportation in general, by the modeling of uncertainties and, if this is not possible, scenario analysis. In the course of our research, we have already published 4 journal publications. We presented at 3 different international conferences, we filed 2 patents, and I also wrote and finished my dissertation. On the following slides, I want to illustrate our stochastic optimization approach using an example from engine calibration. Here you can see a standard calibration formulation as it would be state-of-the-art. One such typical optimization goal would be to minimize a weighted sum of fuel consumption and/or emissions, where the cost is defined on one specific drive cycle, which is defined by engine load and speed. This drive cycle gives us then representative operating points and corresponding weights. And we are looking for the engine parameters U, I, for each operating point individually. The most important shortcoming of such an approach is the dependence of the calibration on just one cycle. This means that the calibration might perform very well on this one cycle, but potentially very poorly on different cycles. Another issue comes from the fact that perfect operation of all the components within the engine is implicitly assumed here. Therefore, in order to fix these issues, we introduce our extended stochastic formulation, where we add random disturbances to the operating points and to the engine parameters. The disturbances epsilon x are disturbances in the engine operating space, which is defined by engine speed and load, and they can be interpreted as random motion around the representative operating points. That way, we are getting rid of the dependence on just one cycle, and we can instead use distributions of cycles in the engine operating space and describe typical vehicle usage. The disturbances epsilon u are simply actuator errors or control inaccuracies within the engine. With this stochastic formulation, we can formulate a new optimization goal. In this case, we want to minimize the expected value of our cost distribution, subject to various constraints. A solution of this problem is then obtained as follows. First, we need to model or estimate the distributions of all the relevant disturbances. From that, we obtain the objective distribution, from which we want to then calculate the expected value. This is typically not possible in an analytical way. That's why we need efficient tools to approximate this expected value. Once we have an efficient approximation, we can then simply minimize this expected value using an ordinary optimization solver. With that, let's jump directly to the results. Here we are comparing 4 different calibrations. This means that 4 different optimizations were performed in order to be compared with each other. The versions A and B follow our stochastic optimization approach, just using different approximation techniques. A uses our own development, a very efficient Taylor approximation of the expected value. B uses an ordinary Monte Carlo simulation. The versions C and D are deterministic state-of-the-art approaches where only one drive cycle and no uncertainties are considered. Once we have performed those 4 optimizations, we can compare the resulting calibrations by evaluating the cost function on a set of validation drive cycles together with a set of simulated disturbances. And by doing that, we obtain these 4 distributions of the cost. We can see that the stochastic optimizations clearly outperform the deterministic versions C and D. The entire mass of the cost distribution is shifted to the left by the stochastic optimization approach. Furthermore, it was observed that our developed Taylor approximation delivers virtually the same result as the Monte Carlo simulation while being much faster. This means that we can achieve the same accuracy while dramatically reducing the computational effort. The presented stochastic optimization approach was not only published in 2 journal papers, it was also already patented and implemented in a commercial product of our industrial partner A4L. One very important aspect of the presented stochastic optimization approach is the use of large quantities of realistic drive cycles which represent typical vehicle usage. However, the collection and measurement of such cycles during real-world test drives is extremely time-consuming and therefore expensive. That's why we developed a tool to generate artificial but still realistic drive cycles on our own. In particular, we are interested in generating cycles that fulfill all the European RDE criteria for RDE, real driving emissions, testing. For that purpose, we developed a completely new cycle generation algorithm which is capable of producing large quantities of RDE cycles, such as these. With our developed cycle generation tool, we can create arbitrary numbers of artificial, realistic-looking drive cycles. And if we want so, we can have them RDE compliant. These cycles can then be used for simulation or testbed runs, for calibration tasks, like for example the one we saw before, and also velocity predictions. In terms of velocity predictions and the cycle generator itself, we published 1 journal paper and 1 conference paper. Furthermore, the cycle generation tool was also patented with our industrial partner A4L. To sum up, we clearly saw that uncertainties arising in the real-world operation must be incorporated in the calibration process of automotive powertrain systems In order to reduce the risk of overfitting, in order to save cost and time, and in the case of RDE compliant calibration, also increase the probability of passing the type approval tests. We did that by stochastic optimization, and our cycle generation tool was basically a byproduct of that. The academic output of the last couple of years within this part of the research project was 4 journal publications, 3 conference publications, 2 patents, and also 1 dissertation. Future research may be centered on dynamic operation and the dynamic modeling of uncertainties. In that respect, also the development of highly efficient and distributed optimization solutions is required. I hope this short presentation has sparked some interest in our research work. If so, please feel free to contact us at any time.